Hello, I'm Rose, and thank you for joining in. I'll talk about trying out different additives in Ethylcellulose oleogels. It's unfortunate that I couldn't be there in person. I'd like to thank the event coordinators for being very accommodating and setting up my poster instead. One good thing about this is I can show you lots of different pictures. So here we go. What is an Ethylcellulose oleogel? So what we've done here is similar to making jello, but out of oil and polymer. As you know, cellulose is a polymer chain that has long strand of glucose units. And ethylcellulose is one of its derivative forms. It forms a crystalline network and it traps oil inside, as you see here. Ethylcellulose is unique among different cellulose derivatives, since it's the only known polymer to date that can structure oil directly. Why is this study important? You might ask. It's quite widely known that saturated and trans fat can have negative health effects. If you can make solid fats from vegetable oils, without the trans esterification and hydrogenation and stuff, it might be able to replace them as a healthier option. And the second reason we are actually putting additives to the easy gels is because in its nature it's very brittle. So when the gel is deformed, the oil leaks out and the structure doesn't reconnect again. So if you see here in the pictures, you can see the oils leaking out to the center. This is not a very desirable quality, as one of the things that we seek from a solid fat is this mouthfeel that gives us the texture, the plasticity. So adding an additive can help this. They are we usually add surfactants. They have partially polar regions and non-polar regions. They can go in between the EC chains because EC is a polymer, so they're much, much bigger than these small surfactants. So their head groups can interact with the polar groups in the EC chain, and if they have the right size and the right properties, they may act as a plasticizer that allows the chains to slip past each other and rapidly recover the hydrogen bonds in between them so that the oil doesn't leak out. But it might also have other different effects. So we are screening the types of additives so that we can take a closer look at them in the future studies. Here are the list of additives that we've used. Most of them are surfactants, but we also use waxes. Surfactants are amphiphilic molecules that have both polar and non-polar regions. Waxes are esters that of fatty alcohol and fatty acid. As for the method, we heat 8% EC and oil and a bit of TBHQ as an antioxidant. We heat them for 10 minutes after it reaches 160 degrees Celsius. After that, we portion them into vials and add roughly half quantity of the EC of the additive. So in a vial, there are 13 grams of oleogel. We need about 4% additive. So we add 0.52 grams of additive in each vial. After that, we reheat them in an oven and invert them a few times to mix properly. And we turn off the oven and cool them slowly inside the oven. After that, the gels are punctured with an 11 millimeter diameter cylindrical probe. It moves 1 millimeter per second and punctures 15 millimeters deep inside into the gel and measures the resisting force of the gel coming up backwards. So probe goes here, the gel tries to come up. So we call this the back extrusion force. And the latter half of the test is averaged to compare between the samples. And a small amount of the gel is sampled on sides with a cover glass and reheated in the oven, cooled down slowly again. This gives them two layers that they can start nucleating. So we have to keep in mind that the crystal grows vertically, and we get to see those pictures. Here are the results from the texture analyzer. It shows a different shapes of graph, but we categorize the graphs like citrum as the brittle gel because it shows that there's some resistance as it goes through and push through the layer. Resistance, push through. And so we're thinking that's not the plastically deforming gel, so we call them brittle. Here are all the graphs. The control is down here, so you can see some additives are really increasing the end strength and also changing the graph shape, the peak location. And here are the pictures that I took with 600 times magnified pictures with the bright field microscope. Note that the y-axis here is in different scales for each graph, and you can see some has needle-like structure. This is more like a feather. You could say this is really hard to tell what kind of structure is in them. You can see how they are different. And this is the average back extrusion force graph, going from 7.5 millimeters to 15 millimeters deep. In conclusion, the additives change the average back extrusion strength greatly, as S-stem here is show the weakest gel strength. It decreased almost 90% compared to the control, whereas behenic acid at the end, it increased the gel strength to become almost 7 times the control gel's strength. So that's a difference. And the microscopic structure varied between the additives. Some showed crystalline structure, like the things we talked about, the needles, and some showed the particles, like rice bran here. Some showed feather-like structure. Some are really hard to tell. One thing that we could find some trend is if you can see some kind of visible structure in the microscope, it appears turbid, but it didn't really connect to the strength of the gel itself. So carnauba wax here, rice bran wax, they have similar microscopic structure, looks turbid, but have very different strengths. And although lauric acid is really clear like the control oleogel, it still increased its strength more than the carnauba wax. So it's hard to tell what kind of connection is in between the structure and the gel strength from these results. One thing that might be interesting to look at is the behenic acid, behenic alcohol, and their mixture. The graph changed, showing only one peak. The average strength decreased in each of the components. And the microscopic structure also changed, almost like a mixture of them. It is their mixture. For future studies, we could look into the structure with a different microscope, like differential interference, contrast microscope, or polarized light microscope to get a better image of the structures or the crystalline regions. We can also look more into the composition of the waxes because most of them are mixtures of different chain lengths. Yeah. So that's the end of my presentation. Thank you for listening to the end. If there are any questions or if you'd like to see other pictures, please let me know and send an email. I'd like to thank Dr. Gravel for guiding me through the experiments. And providing me with interesting topics and thoughts to look at. As an exchange student, I had a great time at UC Davis, and I would also like to thank all the professors and friends that helped not only expand my knowledge, but grow as a better person. Thank you, everyone, and have a nice day.